Good morning, students. I hope everyone is doing well. I'm very happy to meet you all again. Stay safe and healthy at home. Don't go outside unnecessarily. Make use of this time wisely for your studies. Take care of your health also. Yesterday we discussed and we revised the first lesson, metallurgy, fully. I hope you all revised the first lesson thoroughly once again. Today we are going to start the second unit, P block elements part 1. Actually, this P block elements we have from 13th to 18th group in the periodic table, so we cannot study all together in one unit itself. So this P block elements has been divided into two units. Second unit we are going to learn it as part 1. Third unit you are going to learn it as part 3, part 2. Is it clear? So in this first part you will be learning about the elements from 13th to 15th group. Remaining groups will be discussed in the third unit. Is it clear, children? We are going to start the lesson now. So you all know very well, this is the periodic table. So on the left side of the periodic table you can see the S block elements. The right side, the highlighted one, we call it as P block elements. In between the S and P block you can see the D block elements, and at the bottom we have the F block or inner transition elements, and D block elements are also called as transition elements. Now, how we are placing the elements here in the respective blocks, S block, P block, D block, like that. So when you write the electronic configuration, if the last elements enters the S subshell, then the electron, that particular element will be placed in the S block. In same way, if the last electron enters the P subshell, then that particular element will be placed in the P block. So this is how the elements were divided into 4 different blocks in the periodic table as S, P, D and F. So today we are going to learn about P block elements in detail. One speciality about this P block element is this P block element has metals, non-metals and metalloids. If you take the other blocks, S block is completely metal, F block and D blocks are also completely metals. This P block elements alone are having metals, non-metals and metalloids. Now we are going to see some general trends which we are going to use throughout the lesson. So let us remember few general trend in the periodic table alone. So if you take the periodic table, as you move from top to bottom, the atomic radius increases because the atomic number increases. Atomic number is increasing means what? The number of electrons are increasing, which makes the number of shells to increase. As the number of shells increase, the atomic radius increases. So from top to bottom, atomic radius increases. And same way, if you take the ionization energy, what happens to the ionization energy? From top to bottom, the ionization energy decreases. What is ionization energy, children? The amount of energy required to remove an electron. We call it as ionization energy. Why it is decreasing from top to bottom? So as the atomic radius increases, the electrons in the outer subshell, they are not in complete contact with the nucleus which is present at the center. So they don't have proper attraction. If there is complete attraction means you cannot separate the plus and minus charge. The minus charge here I am referring as electron, the plus charge I am referring as nucleus. So as you move from top to bottom, ionization energy decreases means atomic radius which is increasing makes the ionization energy to decrease because the electrons are not closely with the nucleus, they are away from the nucleus, so that they are not attracting each other, so we can easily remove them. Therefore the ionization energy decreases from top to bottom. As you move from left to right, the atomic radius decreases, which makes the ionization energy to increase. Because atomic radius is small means what happens? The electrons are in good contact with the nucleus. Therefore, the attraction will be more. Therefore, ionization energy will be increasing. You have to supply more energy to remove an electron from the outer subshell or the whatever you're going to remove. Is it clear? So this is how you have to remember. Top to bottom atomic radius increases, and then top to bottom ionization energy decreases. From left to right atomic radius decreases, and top to bottom, left to right ionization energy increases. Is it clear? Now let's see. So in today's class we are going to discuss about the p block elements in electronic configuration, metallic nature, ionization enthalpy, electronegativity, anomalous properties of the first elements, and then inert pair effect followed by allotropism in p block elements. So if you take the periodic table, you all know very well, we can place the elements in the p block when the last electron enters the p subshell, then we call them as p block elements. This p block element has been divided into 6 groups starting from 13th to 18th group. So from boron to helium. So these elements, they have quite varied properties, and this block contains, as I told before, it has non-metals, metals and metalloids. And elements in this particular particular block plays an important role in our daily life. For example, if you take oxygen, we cannot imagine our life without oxygen. And then if you take aluminium, you can see aluminium right below the boron. Okay, so if you take aluminium, which has plenty of applications, like from household utensils and parts of aircraft, everything, it is made up of aluminium. And if you take silicon, germanium, which are all these semiconductors, so it is must that we need to know the properties of these elements because we are using them in our daily life. So we are going to discuss that only in this lesson, how it is useful and how it is reacting, what are all its physical property, what are all its chemical property uses. All this we are going to discuss in this lesson. Now if you take, first we are going to discuss about the electronic configuration and oxidation state. The very common electronic configuration of p block elements is ns2np126. Like if you see this table, what is the atomic number of boron? It is 5. So when you write the electronic configuration, it will be 1s2, 2s2, 2p1. So you can see the valence electron, outer electronic configuration, it is 2s2, 2p1 for 13th group, which is boron family. Is it clear? So that is what we have written here as ns2, np1. Now for example, 14th group is carbon family. The atomic number of carbon is 6. When you write the electronic configuration, what is the electronic configuration? 1s2, 2s2, 2p2. Therefore, the outer electronic configuration will be ns2, np2. N is common. N is the principal quantum number. It could be 1 or 2 for S, and 1, 2, 3 for the p block element. So it could be anything. Now the 15th group is our nitrogen family. The atomic number for nitrogen is 7. When you write the electronic configuration, it is 1s2, 2s2, 2p3. Therefore, the outer electronic configuration will be ns2, np3. So, if you take all these outer electronic configuration for all the groups, first this ns2 is same. Yes or no? The second part in np, it is varying as 1, 2, 3, 4, 5, 6. So how will you write the general electronic configuration? ns2, np, 1, 2, 6. So that is what it is given here. Here ns2, np, 1, 2, 6. Is it clear? The elements of group 18 are completely filled and they are least reactive. So whenever the orbitals are completely filled, then they will be least reactive. So when they will be highly reactive, if the orbitals are incomplete, if it is not octet, then it will go and react with the other element to make it as completely filled. So here if you take this group 18, which are inert gases, they are completely filled here. So helium, neon, argon, krypton, it is here. Xenon, they are completely filled, therefore they are very least reactive. So reactivity is based on, like, for example, if you need a pen, you have to open your mouth and ask your friend, I need a pen. That means, which means you are reacting towards someone for something. The same way, if you are having pen, if you are having enough pen with you will not go and talk, which means your reactivity is less. Same way, when the electrons are completely filled, the elements will not go and react with the other elements. The elements of this block show variable oxidation state, and the highest oxidation state is equal to the number of valence electrons present in them. So as you can see here, number of valence electrons, already we have written the outer electronic configuration, which is our valence electrons. So here the oxidation state also is equal to that of the valence electrons. So for 13th group it is +3. For 14th group it is 4 electrons in the outer shell, which is +4. The 15th group it is 5 electrons in the outer shell, which is +5. Is it clear now? So that is what they are saying here. The elements of this block show variable oxidation state. It is equal to that of the valence electrons. Valence electrons means what? Elements in the outermost orbital, we call it as valence electrons. But if you take the S block elements, unlike the S block elements, we cannot expect only the positive oxidation state. If you take S block elements, what are the S block elements? Alkali metals and alkaline earth metals. The oxidation state for alkali metals are +1. Alkaline earth metals are +2, which is very common throughout the group. But if you take this P block element, they show negative oxidation state also. Is it clear? So why? Because you can for example, you can take halogens. These halogens are highly electronegative. Electronegative means what? Tendency to attract the shared pair of electrons, we call it as electronegative. For example, if you take fluorine, the atomic number of fluorine is 9. So when you write the electronic configuration, simple electronic configuration, in the K shell you will write put 2 electrons, okay, and in the next subshell you will put the 7 electrons. Is it clear? So 2,7 will be the electronic configuration. I'm saying this simple electronic configuration. So 2,7 will be the simple electronic configuration for fluorine, whose atomic number is 9. How will it make it octet? So in the outer subshell it is having only 7 electrons. How will it make it as octet? So it has to gain one more electron to make it as 8. So this fluorine will always go and attract the electron. Here in chemistry, if anything is having enough electrons, we will be mentioning it as negative sign. If it is lacking electron, we will be mentioning it in a positive sign. So here I told now the electronic configuration of fluorine is 2,7. To make it as octet, it is going to attract one electron from the other element, whose oxidation state is going to be -1, because it is having one electron extra. Is it clear? So if you take throughout the halogens, all the halogens will be having the oxidation state as -1, which is given in the second point here. Similarly, the other elements belonging to the pnictogen and chalcogen group also show the negative oxidation state. So first we need to understand what is this pnictogens are. So group 13 elements are called as icosahgens. So the group 13 name is icosahgens. 14th group is tetragens. 15th group is pnictogens. 16th group is chalcogens, and 17th group is halogens, and finally we have inert gases. So what they are saying here, last point, the other elements belonging to the pnictogen and chalcogens groups show negative oxidation state, which means the 15th and 16th group also show negative oxidation state. 17th group completely show negative oxidation state. Is it clear, children? Are you all clear with this electronic configuration and oxidation state? Next we have is metallic nature.